Today we will discuss about the relation between Cp and Cv. We know that what is Cp? Cp is heat capacity at constant pressure. So Cp is equal to del H upon del T at constant pressure. What is Cv? Cv is heat capacity at constant volume. So Cv is equal to del E upon del T at constant volume. Del E, change in, what is del E? Del E is change in internal energy. And what is del T? Change in temperature. And similarly, what is del H? Del H is change in enthalpy. And what is del T? Change in temperature. So these are these equation number 1 and equation number 2. The magnitude of Cp and Cv are different for a gas. So the value of Cp and Cv are different for a gaseous material, and it may be equal for these may be equal for solids and liquids, but for water Cp and Cv are different. But mostly in case of gases, Cp and Cv are different. Heat absorbed at constant volumes increase internal energy of gas, and heat absorbed at constant pressure is used in doing some external work in addition to increase in internal energy of the gas. So we can say that heat absorbed at constant volume only increase the internal energy of a gas, while heat absorbed at constant pressure is also used in doing some external work. And so we can say it increase in internal energy of the gas, as well as it is used in doing some external work. So more heat is required at constant pressure than at constant volume. So we can say Cp is always greater than Cv, or del H is always greater than del E. From equation 1 and 2, if we subtract equation 2 from equation 1, then we get equation number 3. So we get Cp minus Cv is equal to del H upon del T at constant pressure minus del E upon del T at constant volume. And you know what is the relation between enthalpy and internal energy? The relation is H is equal to E plus Pv, and we can give this equation number 4, and if we differentiate this equation number 4 with respect to temperature at constant pressure, then what will happen? We get equation number 5. What is equation number 5? We get del H upon del T at constant pressure, because we are differentiating this equation with respect to T. So we get in LHS del H upon del T at constant pressure, and which is equal to del E upon del T at constant pressure plus P. P is here constant, because we are differentiating this equation at constant pressure. So P is constant and it remains constant, and we differentiate V with respect to T at constant pressure. So we get P bracket del V upon del T at constant pressure. Putting the value of del H upon del T P from equation number 5 to equation 3, we put the value of del H upon del T at constant pressure from equation number 5 to equation number 3. So what we get? We get another equation number 6. So we put the value of del H upon del T at constant pressure, then we get equation number 6, Cp minus Cv is equal to del E upon del T P plus P del V upon del T minus del E upon del T at constant volume. At constant pressure, internal energy is function of volume and temperature. So we can say E is function of volume and temperature, and so what will be d will be equal to del E upon del V at constant temperature dV plus del E upon del T at constant volume dt. So we differentiate E with respect to V at constant temperature and multiply it with dV, and in the second term we differentiate internal energy with respect to temperature at constant volume and multiply with dt. So we get equation number 7. Dividing equation 7 by dt at constant pressure, this equation is divided by dt, and we apply the condition of constant pressure, then we get equation number 8. Del E upon del T at constant pressure, del E upon del V at constant temperature remains as it is, and dV is divided by del, it becomes del V. Del V divided by del T at constant pressure, and plus del E upon del T at constant volume remains it is, and dt divided by dt becomes 1, becomes unity. So its value is not write down here. From equation 6 and 8 we get what is equation number 6. This is equation number 6. Cp minus Cv is equal to del E upon del T at constant pressure, and this term, the value of this term is derived by equation number 8, del E upon del Tp. The value of del E upon del Tp is put in equation number 6, and we get equation number 9. And here del E upon del T V, one term is positive and one term is negative, so both terms are cancelled out, and what we get next, we get Cp minus Cv is equal to del E upon del Vt, del V upon del T at constant pressure plus P del V upon del T at constant pressure, and we take del V upon del T at constant pressure is common, the bracket P plus del E upon del V at constant temperature. So we get equation number 11. Equation 11 shows the general relationship between Cp and Cv, which is applicable for solid, liquid and gas as well. So this is equation 11 is applicable for all type of material, solids, liquids and gases. And in equation 11, del V upon del T at constant pressure is the measurement of work done by the system, whereas del E upon del V at constant temperature is the measurement of intermolecular attraction in the gases. In gases, intermolecular attraction is negligible as compared to liquid and solids. Or for ideal gas, because there is no force of attraction between the molecules, among molecules, so del E upon the value of del E upon del V at constant temperature will be 0, because for ideal gas internal energy only depends on the temperature, it doesn't depend on the volume of the gas. So del E upon del V at constant temperature will be 0, and if we put the value of del E upon del V at constant temperature in equation number 11, then we get Cp minus Cv is equal to P del V upon del T at constant pressure. So we get equation 11, equation 12. For 1 mole of an ideal gas, PV is equal to RT, because n, the value of n is 1, so PV is equal to RT. And if we differentiate this equation 13 with respect to temperature at constant pressure, what we get, because we are differentiating at constant pressure, so P is a constant, and if we differentiate V with respect to T at constant pressure, then we get equation P del V upon del T at constant pressure is equal to R, and del V upon del T at constant pressure is equal to R upon P from equation 12 and 14. If we put the value of P del V upon del T at constant pressure is equal to R in equation number 12, then Cp, we can say that Cp minus Cv is equal to R, and thus the difference between Cp and Cv is equal to universal gas constant, which is R, for 1 mole of an ideal gas. So I think you understood what I taught, and please like and share the video. Thank you so much.